The left-hand side is Earth, the right-hand side is the rocket. And again, there's agreement over the speed here. There's disagreement over what's actually moving that fast. All right, I'm going to attempt to do what I was trying to do before, and hopefully a little bit more coherently. We know what our result's going to be. And I did not put it back. And nope, there it is. Questions before I erase this? And I will get to probably the most mind-blowing thing of it all coming up. Earth, planet X, rocket, zipping along over there. So from Earth's point of view, the rocket is traveling at some speed, beta c. From the rocket's point of view, the planet is traveling at some speed, beta c. So this would be Earth's point of view and rocket's point of view, where we have rocket and planet X is traveling towards it at v is equal to beta c. Earth claims how far X is away. It has that distance, it has that proper length there, and it's saying that the length of planet X from Earth's point of view is equal to how fast the rocket's traveling, the velocity or speed of the rocket from Earth's point of view, times the time from Earth's point of view. The speed here is just beta times c, whatever the fraction of the speed of light it is, times the speed of light. So it's just beta c, the time from Earth's point of view. I should say that is the time, not just from Earth's point of view, that is the time that the rocket is traveling from Earth's point of view. So time rocket is traveling from Earth's point of view. Let's throw a little r in there. It's time the rocket from Earth's point of view. Down here, the distance to the planet from the rocket's point of view would be equal to the speed of the planet from the rocket's point of view times the time of the planet from the rocket's point of view. And again, the speed of the planet from the rocket's point of view is the same as the speed of the rocket from the planet Earth's point of view. So this is beta c times t x r. T sub, this is a subscript. Now I do have beta and c common to both, so I'll solve for beta and c. So beta c is going to be equal to L x e over TRE. So this is the distance to planet X from Earth's point of view and the time that the rocket is traveling from Earth's point of view. And that's equal to the distance that planet X travels from the rocket's point of view over the time that planet X travels from the rocket's point of view. So if we solve for LXE, the distance the planet is away from Earth's point of view, that's going to be the distance the planet is away from or the distance the planet travels from the rocket's point of view times the time that the rocket travels from Earth's point of view over the time of the planet from the rocket's point of view. We have these two times here. One of them is the proper time and one of them is not. Recognize the time from the planet is traveling towards the rocket. From the rocket's point of view is, well, they're looking at their stopwatch when the planet starts to move, and they stop their stopwatch when the planet gets to them. This is the time in the rest frame of the rocket. This is not the proper time because this is the time that the rocket is traveling. From Earth's point of view, the rocket is moving. Therefore, the rocket is not at rest, and therefore, this is not the proper time. So L, the distance the planet is away from the Earth's point of view, is the distance the planet moves from the rocket's point of view times time over proper time. And that is just gamma. And as we established, this is the proper length. So that would be the other length times gamma, which is what we have written right here. Questions to hear before I really blow your minds? Then let's do it. Simultaneity. All right, so we now have introduced the concept that length is not the same depending upon, length is not absolute, time is not absolute. There's pretty much only two absolutes. We'll get to that in a moment. All right. So here's the thought experiment. I have a train here. I have a detector in the train that is exactly in the midpoint of the train. It's going to detect light. I have something that's going to flash here, something that's going to flash here. On top of the train, I have Lou. Meanwhile, over here on the side, I have Sue. Lou and Sue show up in a lot of problems. They were conjoined twins, connected at the toenail. They easily got separated, but they were born at the exact same time. Now, when the middle of the train car, in essence, the detector is the closest point to Sue. So when the train is here, Sue says these two things flash at the exact same time. So we have this flash going off here, flash going off here. Sue knows they go off at the same time because she can measure it, that light gets to her at the exact same time. Now the detector is going to either show one of two colors after the experiment's over. This detector will do red if the left flash gets to the detector first, or it's a tie. It's going to be green if the right flash gets there first. All right, so the train's going to move along. These two flashes go off at the same time. Sue is watching it, and she knows that they go off at the exact same time because she's got her own detector, light gets to her at the same time. And so now they have two different points of view. From Lou's point of view, Lou claims, so these are the predictions that Lou and Sue both make. One of them is correct, and one of them is not. So the first question is going to be which one of them is correct, and the second one is why is the other one not? How can they be explained? So from Lou's point of view, that if these flashes go off at the exact same time, from my point of view, we're all at rest. So all at rest. He's not moving, Sue is. So if these two flashes go off at the exact same time, then, and they're both at rest, they should both get to the detector at the exact same time, so the detector will be red because it's a tie. Sue's point of view, she says, no, these things, if these things go off at the exact same time, then if we look at the moment here, so they go off at this time, so I now have light flashing in all directions, but I only care about the light that's going towards the detector. So the light from the left is going to be traveling to the right, light from the right is going to be traveling to the left. And the detector is moving towards the right, and so because the light from the right is going this way and the detector is going that way, Sue claims the right light will hit it first, and so it will be green. They run the experiment, they stop the train, and they look at the detector, and they see a color. It's green. Sue is correct, Lou is not. What is wrong with Lou's thinking, or how on earth could Lou's thinking be wrong? I mean, if Lou is wrong, what else has to be true? And I open it up to the class to figure it out. So first, any questions about the problem? Okay? Now my question of the solution. Why is it green? Or what has to be true if it is green? All right, let's do it from this. I'm going to have flashed oil on the two walls. I put a detector smack dab in the middle, perfectly aligned. If they flash at the same time, the light will get to the detector at the same time. Does that make sense? Yes. Okay. So therefore, from Lou's point of view, everything's at rest relative to him. Detector smack dab in the middle. What happened? Lou's wrong. Well, there's something wrong with Lou's point of view. Or I should say something different about Lou's point of view.
Lou's point of view is wrong because he's not at rest.
He is at rest relative to the two things that are flashing in the detector.
Yeah. But the distance changes within his frame.
What do you mean?
Like the distance that the light has to go on the right side is less than the distance that the left side has to get to the detector.
How can that be Lou's point of view?
Well, it doesn't make sense in his point of view.
But in fact, it does. It is green. I mean, from his point of view, it's not an issue with the distance. From Lou's point of view, the distance from the left side to the detector is the exact same as from the right side to the detector. They are indeed both at rest relative to him. Or both, all three, the two detectors, all four. Two detectors, Lou, and one detector, two lights, and Lou are all at rest relative to each other. That does not change. After they've done the experiment. Look at it from Sue's point of view. Sue is traveling this way. When she passes the halfway point, or when the detector is even with her, the two flashes go off. From Sue's point of view, or actually from the train's point of view, the train's traveling this way, it makes sense that that light would get there first. The one she's going towards will get towards faster than the light chasing after her.
Is it this, like the space that the light takes up is independent of like the whole train?
No, so the fact that the light just goes out in every direction? Is that what you're saying?
Like from the point that the flash happens, like that little like space in the beginning is independent of the train itself moving, so it like stays fixed technically, like in like a way that the train is moving independent of the area that the light is already like taken up.
No, it's not the right path. Slightly different point of view. We know, based upon the experiment, and assume the experiment went correctly, even though it's a physics experiment, we know that it's green after it's done. Which means that the right light got there first. How can that be? How can the right light get to it first? If, from the detector's point of view, the two lights are at rest, how can the green get there first? And the solution, once you know it, is so incredibly obvious. But it requires you to sort of stretch your mind a little bit to get there. It's wintertime. Daniel is perfectly in the middle between Ian and me. We have snowballs in our hands, and we're both going to throw them at Daniel. The snowballs will be launched at the exact same speed. The speed is the same, distance is the same. We're all at rest relative to him. Snowballs aren't, but we are. Ian's hit Daniel first, and then mine hits him. How is that possible?
The force has applied.
Pardon?
It has to do with force being
No.
applied.
His seems like it's going faster because we have to be having a velocity altogether going that way.
Yeah, except again, I mean, we're all at rest relative to each other. That's the key thing. This is Louis' point of view. We're all at rest relative to each other, which is a true statement. How on earth could Ian's snowball get there first if they were the same distance and they go at the exact same speed?
Were they thrown at the same time?
Ah! What in the scenario here with Ian and me, who would have thrown first? Yeah. All right, over here. From Lou's point of view, which light went off first? Yes. It showed green, so the right one had to get there first. They are indeed all at rest relative to each other. And only way that it would not be a tie is if the green one goes off first and then the red one. But Sue insists they went off at the same time. And she is correct. They did go off at the same time, according to Sue. They did not go off at the same time, according to Lou. Just because two things happened at the same time in one reference frame does not mean they happened at the same time in another reference frame. That is the secret to this. So we now have not only time not the same, length is not the same, and matter of fact, the way things happen, the order in which things happen is not necessarily the same. We're running out of things that are going to be the same. So what is the same for no regardless? Well, we've talked about one thing. What is one thing that we've talked about that is the same for everybody?
Speed.
Of
Like,
there we go. As a group, we got it. All right, speed of light is the same for everybody. Speed of light. The other part about speed that, like the muon and mountain, that the scientists and the muons agree on speed, they disagree on what's traveling that speed. And so I was considering that not the same thing, because one's saying, hey, the Earth's moving at that speed, the other one's saying the muon's traveling at that speed. You can get into a semantics argument on that one, but officially, the speed of light is going to be the same regardless. The other thing that is the same, let's go back to the mirror experiment. That was the box that was traveling off to the right at some speed v, and it shoots a light up, and the box gets to it. So this was at the lab frame. And then in the rest of the box frame, or the rest frame, light travels up and back. I know that speed, sorry, ordered that way. Because this object's moving that way, this distance here is the same for both.